Hello everyone, welcome to my overview session talk. So this talk will be about emotion for speech synthesis. I am Berrak and I am an assistant professor at Singapore University of Technology and Design. So let's start with the content. I will briefly introduce the research direction, and then I will be talking about voice conversion, followed by emotion in voice conversion, such as expressive voice conversion and emotional voice conversion. And after that, I will be talking about emotion in speech synthesis. And last but not least, I will be talking about some data sets and a data set that we proposed very recently called emotional speech dataset. So let's start with the introduction. To start with, today's AI mainly focuses on IQ, and so does the speech synthesis. And if you think about it, the state-of-the-art speech synthesis frameworks is optimized to convert text content to natural speech. And unfortunately, this is not ready for real-time human-machine dialogue. So today's speech synthesis frameworks do not attempt to understand and express empathy. If you think about it, we communicate through speech. We express meanings and feelings through speech. And we were able to do that even when we were kids. On the other hand, machines are still unable to do the same in a human-like manner. An effective, engaging, and cooperative human-to-human conversation includes so many aspects, such as communicating with kindness, expressing empathy, agreeing, disagreeing, to seeking common ground, or even to seek understandings and feelings more than just being right. So we expect machines to do the same in a human-like manner, but they are unable to do this. So with our team, we study the theory and practice that enable such speech synthesis. So an expressive speech synthesizer should understand our emotions and the dialogue context so as to speak like a human with both meanings and feelings. To achieve that, we develop deep neural network-based computational models for speech styling, such as expression of emotion, empathy, and entrainment to improve the level of engagement in a dialogue. And I do believe that machines' ability to speak like a human in a live conversation will mark an important step. So if you think about it, expressive speech synthesis technology can be widely used in so many real-life applications, from human-machine communications to robotics, call centers, games, entertainments, as well as healthcare applications. Later today, I will also show some specific applications that we can achieve through this research. So before doing that, let's start talking about voice conversion very briefly. So this is a research direction that really fascinates me. Our aim is to convert one's voice to sound like another person without changing the linguistic content, and we can achieve that with or without parallel data. So given that we have the source speaker here, we are trying to find a mapping so that we can generate the target speaker. And in voice conversion, we can generate one person's voice with a very limited training data, which is very remarkable. And the success of this voice conversion technology opened up tremendous opportunities for novel innovative products and services. The first thing is medical applications. We can even improve perceptual quality of speech, as can be seen here. So another direction is personalized conversation assistants, or talking heads, social robots, dubbing of movies and games, singing applications, and conversation AI in the big picture. So I would like to just show you some of the history of voice conversion. So it was the year 1988. We had the very first voice conversion framework, and it was actually a vector quantization-based framework. So let me share sound here. Okay, so let's listen how it sounds like the very first voice conversion framework.
The groundhog clearly saw his shadow but stayed out only a moment.
So this is the vector quantization method. And after that, we have fuzzy vector quantization.
The groundhog clearly saw his shadow but stayed out only a moment.
And then we have Gaussian mixture models.
The groundhog clearly saw his shadow but stayed out only a moment.
And after many years, we have non-negative matrix factorization, NMF.
One odd detail. All these books were shelved indiscriminately without regard to the language in which they were written.
And with the deep learning era, we also have some deep learning architectures here, for example, DNN.
Anything unusual or abnormal was sufficient to send the fellow to Molokai.
We have a framework called LSTM.
There is more behind this than a mere university ideal.
We have phonetic sparse representation, a framework that combines automatic speech recognition with a non-negative matrix factorization.
One odd detail. All these books were shelved indiscriminately without regard to the language in which they were written.
So more recently, we have GAN-based frameworks, GAN, CycleGAN.
Philip stood undecided, his ears strained to catch the slightest sound.
As you can see, the quality is much better here. And GAN together with a WaveNet synthesizer.
Philip stood undecided, his ears strained to catch the slightest sound.
So I want to highlight that we cannot directly compare these frameworks because they do work under different assumptions. For example, a framework like GMM and NMS, they require less training data, 30-40 utterances from both speakers, whereas this LSTM that is highlighted here required many hundreds of training data, which was parallel, which is not that practical. So we cannot compare them one by one, but what we can do here is that we can see the history and the voice quality that we can achieve through voice conversion research. And some of the applications that we are working on related to voice conversion are also listed here. The first one is singing voice conversion. We can map a singer's voice to sound like another singer, or we can even make you sing perfectly, even though you are not talented. Another direction is deep learning-based singing analysis and synthesis. So the current vocoders, the neural vocoders, they are proposed for natural speech, not singing data. So when it comes to singing, it is more challenging to get a neural analyzer and synthesizer. So this is a research direction that we are also working on actively. So another research direction that is related to voice conversion is automatic voiceover. And automatic voiceover is also known as AVO. And this is a very recent research direction that we are working on. So AVO seeks to generate human-sounding speech with perfect lip-speech synchronization. So you can see this task as a combination of speech synthesis and computer vision, in particular video processing. So this AVO technology will transform the way the movie industry conducts voiceover, and it also enables new applications in entertainment, education, and business. So if you're interested to learn more about voice conversion and applications, here we have an overview paper that is published on IEEE ACM Transactions on Audio, Speech and Language Processing. And this is actually open access, so you can directly go to this link, or you can, just take this title and download the PDF version free. And I just want to highlight some of interesting research directions of voice conversion that, new students can focus on. So I want to highlight that voice conversion achieves expressive voice generation with very limited data. So it is really useful in practical scenarios. And I want to also highlight that we can build novel voice conversion frameworks that help our society and people from all around the world. For example, we can help people whose native language is low resourced, or we can help people who are speaking in a non-native language. We can help people with speaking disability. We can improve their perceptual quality of the speech that they generate. And we can also work on the cases with background noise, which is actually more practical in real life data sets that we have. And last but not least, we can also work on emotional speakers and expressiveness. So throughout the slides, I will be focusing on emotional speakers and expressiveness, as also highlighted here. But I believe all of these are interesting research directions for new students joining this research direction. So let's focus on emotion in voice conversion. And for this part, I divided it into two sections: expressive voice conversion and emotional voice conversion. So let's start with expressive voice conversion. As many of you may know, traditional voice conversion has been focused on speaker identity conversion for speech with expression. So the data sets that we are using in voice conversion, they are just natural emotion, not happy or angry. However, in real life, humans, we are expressive and we express different emotional states in our own styles, right? Sometimes we are happy, sometimes we are angry, sad, or excited. So in a recent paper, we study a technique to jointly convert the speaker identity and speaker-dependent emotional style, which is called expressive voice conversion. So this paper was also accepted to be published at IEEE ASRU, and which will be published actually this month. So I want to highlight that this is a more practical real-life situation, because in our daily life, when we are talking, we are expressive, we show emotions, but the traditional voice conversion frameworks are not focusing on that so far. So in this paper, we propose a framework for expressive voice conversion. So we aim to convert, for example, happy utterances expressed by speaker A to sound like speaker B. So we are not only taking into account the speaker identity, we are also trying to learn how this speaker A presents emotion so that we can also map that to a target speaker. So this is really an interesting research direction, and very limited research has been going on in this research direction. And to do this research, we actually require to have some particular data sets. And today, later, I will also show you a data set that we propose to solve this research direction. So to achieve this, joint framework for speaker identity and emotion style conversion, we propose a StarGAN-based approach. And in our StarGAN, we have a new module called SER. So this SER is actually a deep learning-based emotion recognition module. And through this emotion recognition module, we can actually not only learn the speaker identity, but we can also learn the emotional style of the particular speaker as the source and the target. So here we optimize the distribution of the generated acoustic features to match that of the target features with emotional data. And I want to highlight that with this additional input, emotional style features, our Jest StarGAN learns to project both emotional style and speaker identity into the converted speech. So this is really a real life application, because when we are talking, we have always emotional speech, right? So this Jest StarGAN aims to achieve expressive voice conversion from one speaker to another. And in our paper, we conducted comprehensive experiments. These are just some of the experiments that we conducted. These are the screenshots from our paper. But if you're interested, you can also go to the preprint archive version of our paper. So we conducted voice conversion experiments for happy, neutral, and sad. And we conducted these experiments from male to male speakers, female to female speakers, male to female, and female to male speakers. And we conducted these experiments with many speakers. And our proposed method achieves better results, always, for both intragender and intergender settings, which we believe is remarkable. We also conducted listening experiments, and further evaluation is also reported in the paper for those who are interested. So this was expressive voice conversion, where we were still trying to convert the speaker identity together with the emotional state of the speaker. So another research direction that I would like to talk is emotional voice conversion. So emotional voice conversion is actually different than voice conversion or expressive voice conversion. So in emotional voice conversion, we are trying to convert one speaker's voice from one emotional state to another. So we have a happy speaker here, and we are trying to manipulate the emotion of this particular speaker so that the same speaker sounds sad now. So in this research direction, we have published many papers, and today I will show you 3 papers, and I selected these 3 papers in particular because we also released the codes and speech samples of these 3 papers. So if you're interested, you can directly go and check the websites that I'm going to provide today, and you can, just re-implement the models or manipulate the way you need it. So let's start with the first paper. It is converting anyone's emotion. And I want to highlight that this is an Interspeech 2020 paper. So in this paper, we propose an emotional voice conversion framework that is speaker independent. So very basically speaking, after training, we have a new speaker, and whoever it comes, it doesn't matter. We can perform emotional voice conversion. So this is the very first speaker independent emotional voice conversion framework. And here you can see the publicly available codes and speech samples. You can just follow the instructions there to repeat our experiments. And this framework is actually a VAW GAN-based framework. We have an encoder, we have a generator, and we have a discriminator for spectral features. And we have the same for F0 as well. And I want to highlight that for F0, we are using continuous wavelet transform analysis to get 10-dimensional features. And after that, we are using VAW GAN to learn the mapping. And this framework is very flexible because it can achieve emotional voice conversion for many speakers. So another emotional voice conversion framework that we recently published is seen and unseen emotional style transfer. So you can, just check this GitHub page to download the publicly available codes, and you can directly repeat our experiments. And this paper was actually, this framework is actually published at this year's ICAST 2021. So you can, directly read our paper from ICAST archive as well. So I want to highlight that in this paper, we are trying to do emotional voice conversion, but the task that we are doing is still different. So just imagine that during training, you have neutral utterances, happy utterances, and sad utterances, but you do not have angry utterances at all. And at runtime, you want to generate an angry voice. So is this possible? Can you learn an unseen emotion? So the answer is actually yes. In this framework, we are proposing a method to learn unseen emotion style transfer. And to do that, actually, we have an emotion recognition model here. And we train this model and we obtain these deep emotional features. And these deep emotional features will be a latent representation for our encoder, decoder, and discriminative structure. This is very similar to the VAW GAN architecture. So if you're interested in the implementation details, feel free to check our GitHub page. But I just want to highlight that this proposed framework is very flexible because it can achieve seen and unseen emotional style transfer, which we believe is really remarkable. And in case you have very limited data, this framework can help you solve emotional voice conversion problem. And lastly, I would like to talk about limited data emotional voice conversion, leveraging text-to-speech synthesis. So before going into the technical things, I want to highlight that emotional voice conversion and text-to-speech synthesis, or in other words, TTS, share a common goal. And this goal is to generate high-quality expressive voice. The way they do it is very different, but their goal is actually very similar. And in a paper that we recently published in Interspeech 2021, we propose a two-stage training strategy for a sequence-to-sequence emotional voice conversion. So we basically have two stages. In stage one, we perform style initialization. Here we aim to disentangle speaking style and linguistic content with a multi-speaker TTS corpus. And in stage two, we perform emotion training where all components of the networks are trained with limited emotional speech data. So let's look at how we are doing this, shall we? So the left side is actually training phase one, and it is the style initialization. So here we are using text-to-speech synthesis corpus to learn speaking style through the style encoder. And after the training is completed, we can actually have this emotion training stage. And in this stage, I want to highlight that we are using a very limited training data, and the data is emotional. And the style encoder acts as an emotional style encoder, also called as emotion encoder. You can find the details and how we implement this framework on our GitHub page, as well as in our Interspeech paper. But very basically speaking, if you need to generate an emotional voice, and if you have very limited training data, you can definitely leverage from a TTS framework. And this TTS framework is not an emotional TTS framework. This is just a traditional text-to-speech synthesis framework. And after some fine-tuning and adaptation with very limited data, you can actually achieve limited data emotional voice conversion framework. So as I highlighted, I shared today 3 emotional voice conversion frameworks, and the links for all of them are provided here as well. So for those who are interested, go through these GitHub pages. And there are actually other interesting approaches from recent years, not from my group, but from other groups all around the world. So if you're interested, go through these papers as well. So I do believe all of these papers are novel and they are teaching something new to us. So our recent paper is accepted by Speech Communication, and the title is Emotional Voice Conversion Theory, Databases, and ESD. So if you are interested to learn more about emotional voice conversion, feel free to check our paper, and the preprint version is also available on arXiv. Here we summarizes all the recent and the traditional emotional voice conversion framework. We highlighted the challenges, future directions, and the databases that you can use to pursue emotional voice conversion. And we also release a data set here in this paper, which today I will be showing very briefly. So before going through the database section, I want to highlight speech synthesis and emotion. So let's study TTS a little bit together. So TTS, text-to-speech synthesis, is a technology of converting written text into speech. So I really like to draw simple diagrams. And if you look at here, we have an input text here, and it is hello APSIPA. So through a TTS framework, you can actually generate voices that sounds like human. So of course, the resulted speech is expected to sound natural and expressive. And this is a research direction that we are intensively working on. So before showing you some of the research papers that we have published recently, I just want to show you the history of speech synthesis. So in 1939, we have a generated voice from the Bell Labs, and it is called Bell Labs Water, and this is from the World Fair in New York City. So here you are going to listen conversation between a person and a computer. So let's play it.
Will you please make the voters say for our Eastern listeners, good evening, radio audience. Good evening, radio audience. And now for our Western listeners, say, good afternoon, radio audience. Good afternoon, radio audience.
And we have another sample from Haskins, 1959.
I printed this file without looking at a spectrogram. Can you understand it?
And we have another example from KTH Stockholm from 1962.
Welcome to the Stockholm Speech Communication Seminar.
Or from Bell Labs in 1973.
I can read stories and speak them aloud. I do not understand what the words mean when I read them, but I can guess which words are important and which words are not by rules I have been given.
And from MIT in 1976.
It was the night before Christmas, when all through the house, not a creature was stirring, not even a mouse. The stockings were hung by the chimney with care, in hopes that St. Nicholas soon would be there.
And I just want to, come to a more recent framework, Abacus.
I'm looking for a French restaurant. Something at a medium price
And
near the
this is
shopping
from
center.
2013. So as you can see, the voice quality is just remarkable, like the improvement over voice quality. And as I highlighted, we expect that once we generate a voice, it sounds like human, which means natural, expressive, showing empathy, showing emotions, and so on. However, in most of the state-of-the-art TTS frameworks, the expressiveness of the synthesized speech remains to be improved. So I do believe this is an interesting research direction for those who are interested. And another research direction is modeling the style, prosody, as well as the controllability aspect. And last but not least, understanding and generating accented voice is a challenging task, and very limited research has been conducted. So these are some possible future directions that, interested students or researchers can work on. So I would like to show you a recent paper that we published at IEEE ACM, Transactions on Audio, Speech, and Language Processing. And this paper is actually published this year. So to start with, prosody is one of the defining features of expressiveness that actually makes the speech lively, that sounds like, human voice. And in our paper, we propose a novel training strategy for Takatron TTS that improves utterance level expressiveness of speech. So we implement a system that doesn't require any reference speech or manual selection of prosody style at runtime. So here you can see the main stages of our framework, and we have stage 1, which is emotional recognition, speech emotion recognition training. As you can see here, let me use the highlighter. We have the emotion model training here. The blue color in this figure means training, whereas the pink means already trained networks. So stage 1 is aiming to train this speech emotion recognition module. And in stage 2, we are using this trained SER module to train our TTS. And to do that, we actually have 2 loss functions, the style loss and the frame level loss. I will be showing the technical details in the next page. So after training the TTS, we can actually use our trained TTS model. The input is text, as many of you may know. And for waveform generation, we use WaveRNN in this paper. So to our best knowledge, this is the first study to incorporate perceptual loss into Takatron training for improved expressiveness. And let's, look at the framework that we propose here. So the blue framework that you see here is the TTS training, whereas the pink figure that you see is the trained SER module. So we can obtain different features. You can see this as style descriptor, by the way. So we can have these different embeddings. These are low embeddings, these are middle embeddings, and these are the high level embeddings. And through this, loss frame, together with style loss, we can actually obtain our total loss, and we can train our TTS accordingly. So this paper is actually open access at IEEE, and the title is Expressive TTS Training with Style Reconstruction, with frame and style reconstruction loss. So if you're interested, feel free to check out this paper and listen our speech samples. And here you can see our speech samples as well. This is a GitHub page. And I want to highlight that in this paper, we conducted comprehensive objective and subjective evaluation methods, and we observed that we always achieve better scores compared to the baselines. And our speech samples are evaluated by 15 listeners, and we reported them with 95% confidence intervals. So for those who are interested, please feel free to read our paper. And if you have any questions, you can always reach us. So before ending my talk, I want to very briefly talk about the data sets. So in emotional voice conversion research and in emotional speech synthesis research, you can find a lot of data sets. Like these, the first 4 data sets, they are really good, but they have limited diversity of sentences. And the number 5 and 6, actually they are large data sets, but they contain overlapping speech and external noise. So this is also not very suitable for speech synthesis. And the 7th database contains non-verbal expressions and limited diversity of speakers because we only have 4 speakers here. And CMU and the other data set, as highlighted here, only contains 1 single emotion. So what we want to have is we want to have 10 or perhaps 20 speakers with many emotions and hundreds of utterances, right, to build a speech synthesis or emotion voice conversion framework. So with that motivation, we released a dataset called Emotional Speech Dataset. So this dataset has 350 utterances from 10 native English and 10 native Mandarin speakers. And we have set utterances that are natural, happy, sad, angry, and surprised. So you can actually download our dataset from here. And this was a joint work of the National University of Singapore and Singapore University of Technology and Design. And you can also read the details of our dataset here. The dataset is called ESTD. So thank you very much for listening, and feel free to ask me if you have any questions. Take care, everyone.